Listen, guys, now I'm really worried. This is where I got the shot, the second shot. Look at this. It's glowing. Now I go down my arm, and it gets worse. I have a little dot here, but the worst part, look at the vein in my hand. It glows. That is sick. Why is this doing this? Can someone tell me? Look at that. Look at that. It's glowing. And that's exactly where I got the shot. And now my hand in my vein is glowing. Why the hell is this doing this? What the hell is in this?
To that dot. Oh, jeez, look at that. I've had my vaccine, Rosie. What do you think? What's happening? Come on, shine it on my hand. Oh my God. What have they put in that vaccine? Do you think I should have had the vaccine?
No.
A chemical reaction that produces light within an organism is called bioluminescence. There's a wide variety of luminescent species, including some comb jellies, bacteria, dinoflagellates, fungi, and of course, the firefly. Organisms may use bioluminescence as a defense against predators, as a way to catch prey, or to attract a mate. But how exactly are they producing light? Fireflies express a protein called luciferase, which catalyzes a light-producing reaction. The reaction of luciferase takes place in two general steps. First is the adenylation of luciferin using ATP, and second is an oxidative decarboxylation of the luciferyl adenylate to form an electronically excited oxyluciferin. When the excited oxyluciferin moves back to the ground state, energy is released in the form of light. Although the exact mechanism is not known, the generally accepted mechanism is as follows. Luciferase first binds luciferin and ATP. Magnesium is needed to shield the negative charges on ATP. Luciferin acts as a nucleophile and attacks ATP to form a luciferyl adenylate still bound to the enzyme. Pyrophosphate is released. A residue in the active site of the enzyme then deprotonates the adenylate. The carb anion can now attack molecular oxygen. A ring is formed and AMP is released. This results in a high-energy dioxygenone intermediate. The ring spontaneously breaks and we are left with electronically excited oxyluciferin and carbon dioxide. When oxyluciferin returns to the ground state, energy is released in the form of a photon of light. The excited oxyluciferin can tautomerize into the keto or enol form. Some scientists suggest that these two forms emit different wavelengths of light. Now let's take a look at the structure of firefly luciferase. This luciferase is composed of a single polypeptide chain with residues 4 through 436 making up the large N-terminal domain, and residues 440 through 544 making up the smaller C-terminal domain. The N-terminal domain contains a beta barrel and a 5-layered alpha-beta-alpha-beta-alpha structure. The C-terminal domain has 5 beta strands and 3 alpha helices. A disordered loop connects the two domains. Scientists are not sure exactly how the structure of luciferase allows it to function. They compared this structure to enzymes that catalyze similar reactions, like fatty acid coenzyme A ligase. Certain residues seem to be conserved on parts of the N and C terminal domains. This suggests that the active center is formed when the two domains come together upon substrate binding. This crystal structure of Japanese firefly luciferase is complex with a high-energy intermediate analog. You can see how the two domains came together around the substrate. People have incorporated luciferase into biotechnology and laboratory procedures. Next-gen pyrosequencing of DNA uses luciferase to produce flashes of light that correspond to the addition of nucleotides. D-NTPs are added one at a time, and when the correct nucleotide is added to the template strand, pyrophosphate is released. This pyrophosphate is converted to ATP using the enzyme sulfurylase. The luciferase and luciferin in the medium can react with the ATP and a little flash of light is produced. By recording millions of flashes of light, a computer can sequence an entire genome.